Polar coordinate system. A polar coordinate system is a plane with a point O, the pole, and a ray from O, the polar axis. Each point P in the plane is assigned polar coordinates as follows. R is the directed distance, the magnitude, from O to P, and theta is the directed angle whose initial side is on the polar axis and whose terminal side is on the line OP. As in trig, we measure theta as positive when moving counterclockwise and negative when moving clockwise. If R is positive, then P is on the terminal side of theta. If R is negative, then P is on the terminal side of theta plus pi, in other words, halfway around the circle. We can use radian or degree measure for the angle theta. In this example, we have point A can be located by using the Cartesian coordinate system or polar coordinates. On the Cartesian system, we can go over 4, and we can go up 1, 2, 3, 4, 5. So that's the point 4, 5 with Cartesian. On the polar coordinate system, we have this distance right here. Here's this certain distance, and we have this angle. And with the combination between these two, that locates a unique point A. And actually, we don't use D, we use R for radius of a circle. In example 1, plot the points with the given polar coordinates. We have a length of 2 and an angle of pi over 3. Pi over 3 is right here, and if we put that on a circle of, let's say, radius 3, then that length is 3 right there, and this angle right here is pi over 3. In letter B, we have a point that is on a circle of radius 2 and at an angle of 3 pi over 4. Since this is negative, instead of going on the terminal side, we go halfway around the circle and we are actually back here. So point Q is down in quadrant 4. For letter C, we have negative 45 degrees with a length of 3. So we'd have to put that on the circle with a radius of 3. Each polar coordinate pair determines a unique point. However, the polar coordinates of a point P in the plane are not unique. The coordinates r theta is the same as r theta plus 2n pi. In other words, you go all the way around the circle, you get the same point. And negative r theta plus pi. So you can go in the opposite direction, but then if you go halfway around the circle, you're back to the same point. These all name the same point. In general, the point with polar coordinates r theta also has polar coordinates r theta plus 2n pi, or negative r theta plus 2n plus 1 pi. In other words, an odd value. So if you have theta plus 3 pi, that's really halfway around the circle. It'd be 1.5 ways around the circle. Where n is any integer. In particular, the pole has polar coordinates 0 theta, where theta is any angle. If you have a length 0, that puts you on the pole or on the origin. In example 2, if the point P has polar coordinates 3 pi over 3, find 3 additional pairs of polar coordinates for P. Let's locate P. P is on the third circle, has a length of 3, and is at an angle of pi over 3. That's right there. What if we went on the third circle, went in a negative direction, or negative angle, and that puts us right here. That would be the point negative 2 pi over 3 with a radius of 3. But we want to be up here. We would just have to make this negative 3 negative 2 pi over 3. What if we went in a negative direction and went all the way around to the point right there? How many thirds would that be? That'd be 1, 2, 3 thirds, 4 thirds, 5 thirds. That'd be the point 3, 5 pi over 3, negative 5 pi over 3. What if we were on the third circle, went all the way around past the angle to 4 pi over 3, and then went negative on the line? So we could have negative 3, 4 pi over 3. Coordinate conversion. When we use both polar coordinates and Cartesian coordinates, the pole is the origin and the polar axis is the positive x-axis. By applying trigonometry, we can find equations that relate the polar coordinates r theta and the rectangular coordinates x, y of a point P. In other words, we can take polar coordinates and write them as Cartesian and vice versa. Let the point P have polar coordinates r theta and rectangular coordinates x, y. Then we can make all of these statements. Now this just comes from a right triangle. If that's theta right there, this is the x coordinate, right and left. This is the y coordinate, right and left, if we're looking at that point. And then this is the radius of the circle that we could draw through there. The sine of theta is opposite over hypotenuse. Then if we multiply by r, we can write y equals r sine of theta. The cosine of theta is adjacent over hypotenuse, and by multiplying by r, we get x equals r cosine of theta. Just using the Pythagorean theorem, we have x squared plus y squared equals r squared. That's that one. And the tangent of theta is opposite over adjacent, or y over x. Find the rectangular coordinates of the points with the given polar coordinates. This is r and theta, and we need x and y. The relationship is x is r cosine theta, and y is r sine theta. We need r cosine. We need 3 times cosine of 5 pi over 6, and we need 3 sine of 5 pi over 6. We have to locate 5 pi over 6, which is right there. There's the 5th sixth. So we have negative square root of 3 over 2 and 1/2. This ends up being negative 3 square root of 3 over 2 and 3/2. For the point 2, negative 225 degrees, we want the x and the y. So we want r cosine of theta and r sine of theta. Negative 225 degrees, that's right there. That's 45 past 180. We have negative square root of 2 over 2, square root of 2 over 2. We have 2, negative square root of 2 over 2, and 2 square root of 2 over 2. The 2's will cancel out, so the point is negative square root of 2, square root of 2. When converting rectangular coordinates to polar coordinates, we must remember that there are infinitely many possible polar coordinate pairs. In example 4, we report 2 of the possibilities. Example 4. Find 2 polar coordinate pairs for the points with the given rectangular coordinates, negative 1, 1. So this is x, y, and we want polar coordinates. We want r theta. We can make the statement that r squared equals negative 1 squared plus 1 squared. So r squared equals 1 plus 1, so r equals plus or minus the square root of 2. We have square root of 2 comma something, and what if we make the other one negative square root of 2 comma something? We need the angle. We can pick either one of these, but we can make the statement that r cosine of theta is equal to x. And now we know the radius is the square root of 2 times the cosine of theta is equal to, the x is negative 1. So cosine of theta is equal to negative 1 over square root of 2, and that means that theta is equal to the inverse cosine of negative square root of 2 over 2. Well, the principal quadrants of cosine are 1 and 2, and 3 pi over 4 has a cosine that's negative square root of 2 over 2. So we have 3 pi over 4. Now if we want one of the radius to be negative, then we just have to go in the opposite direction. So that's negative pi over 4 and then go in the opposite direction. That's the same point. Likewise, on letter B, we can have r squared equals 9 plus 0. So r equals plus or minus 3. We could have 3 comma something and negative 3 comma something. Let's look at the point 30. 1, 2, 3, 0. That's 0 degrees or 0 radians. And then if we go halfway around the circle, that's pi. And then if we go in the negative direction, that puts us right back where we started. So negative 3 pi is the same point. Convert the polar equation to rectangular form and identify the graph. On letter A, we have r equals negative 2 cosecant of theta. So r can be written as negative 2 over sine of theta. Now if we multiply both sides by sine, we have r sine of theta is equal to negative 2, and r sine of theta is y. And this is a horizontal line. In letter B, we have to multiply both sides by r so that we can get negative 4r cosine of theta. And that's the statement I want right there, r cosine. On the left, I can replace that with x squared plus y squared. On the right side, I can replace this with just x. Now I can, and that's negative, I can add 4x over and then complete the squares. So we have x squared plus 4x plus 4 plus y squared equals 4. I've added 4 to both sides. This factors into x plus 2 squared plus y squared equals 4, and that is a circle. In example 6, we're going to convert the rectangular equation to polar form. X is r cosine of theta, and that's equal to 5. When we write polar equations, we want it to say r equals. We'll have to divide by cosine. So we have r equals 5 over cosine theta, and that's r equals 5 secant theta. In letter B, we have 3r cosine theta for the x, and 4r sine of theta for the y. That's equal to 8. We can factor out the r, and we have 3 cosine theta plus 4 sine theta equals negative 8. And then divide by all of this. The answer is r equals, not negative, I don't know why I made that negative, that's positive. 8 over 3 cosine theta plus 4 sine theta. In letter C, we have to multiply all this out. We have x squared minus 2x plus 1 plus y squared plus 8y plus 16 equals 17. I can rearrange these to say x squared plus y squared minus 2x plus 8y. We have 16 and 1 is 17. When I minus 17 from both sides, we get 0. X squared plus y squared is r squared. Then we have minus 2r cosine of theta plus 8r sine of theta equals 0. I can factor out an r, and we get r minus 2 cosine theta plus 8 sine theta equals 0. Now r equals 0, or r minus 2 cosine theta plus 8 sine theta equals 0. Now, when we write polar equations, we need r equals. I'll add the 2 cosine and subtract the 8 sine. So we have r equals 2 cosine of theta minus 8 sine of theta. When I look at this equation back here, this is a circle with a radius squared of 17. This equation is just the pole. It's the origin. So that's not the right answer. This is the answer right here.